Hello and welcome to PMCD MATHS Teaching, and my name is Paul McDonough, and I'm going to be looking at graphical transformations in this session. So getting straight into it, I mean, we all probably know how to do those graphical transformations, but it is a tricky one to teach and to do well, I think, anyway. So sequence of teaching, I'll put up there. It's not necessarily you have to do one after another, but I think the best order is that with those functions and the plotting and sketching of what I call the base graphs, linear, quadratic, square root, reciprocal, trigonometric. I missed out cubic, actually. Cubic should be on there as well. You should have covered those before starting to look at the graphical transformations. And as I said, you know, should be something that's in the student's library. They should, in their brain, they should actually be able to recall these base shapes to start off with if they're going to have a chance to be successful with graphical transformations. My rationale for this, okay, so reasons why I go about teaching in this way. I'm going to leave it there for just a few seconds to let you have a read. Okay, so often I said I will get students, particularly at A-level, come in and we talk about graphical transformations. They don't like it, and they'll start giving me rules like, oh yeah, when it's a plus, it moves to the left. You use the opposite direction. They have no real understanding. They just memorised a set of rules to sketch these rather than actually thinking about what's actually happening. You know, and I probably fell into that trap of teaching it that way when I first started teaching, you know, many years ago. Let's give them a set of rules as long as they can do it, you know. But as time's gone by, and obviously when you're teaching A-level for a long period of time, and these are the sort of students you're preparing them for, you want them to have the ability to analyse a function. It becomes very useful at high level work. So how do I go about doing this? Well, going back to the sequence in here, the first part I'm looking at here is exploring transformations with GeoGebra. So I'm a big fan of trying to get the students to construct their own understanding as far as possible. I mean, you can't give it totally over to them, the responsibility, but they can definitely do some of the legwork. And so what I do is normally have a lesson with this where we go on to the GeoGebra, which I'm sure you're all familiar with, but it's there anyway. And it's free, and you know, I usually have laptops. I don't know what your phone policy is like in your school, but you could use phones if that's satisfactory with that. Okay, so what do they do in this? Well, what I get them to do, there's a worksheet which I will attach to this. It's not, you know, it's not mind-blowing, but it does cover the different transformations, and you can see the different transformations that are being covered there. So what I'm trying to get them to do is explain why it happened, explain what they see, and see if they can explain why that's happening. And then at the end of each section, you'll see there's a little sort of assessment for them. Can they now sketch a graph by understanding what they've seen in GeoGebra? And GeoGebra is great. You know, it means you don't have to plot loads of graphs, does it? You know, it means we can actually, by hand that is, we can plot them using the software, and that means they can analyze these patterns very quickly. Okay, so you probably recognize transformations that I'm looking at here. So A, B, C, E, okay, and E and F. Okay. Now, as I said, they should know the base graphs. So, you know, you'll see that sin x popped up in there as well. So before they've done this, I think it's good that they're familiar with that, and it's not a surprise. Although it is a nice surprise when you see what sin x looks like, but it's not, you know, totally unfamiliar for them. Okay, so going back then to that would probably take a lesson, maybe a little bit more, depending on how long you have for a lesson. We have 50 minutes. It's probably going to take me 2 lessons, actually, thinking about that one, if I'm going to do it properly. These then, I remind them and I ask them, I don't like copying very much, but I think they need this library of what I call base graphs, because all quadratics can be drawn from that quadratic graph and so on. We can actually get sketches just by thinking about where to start. So it gives them somewhere to start with their graphical transformations. And then sin x and cos x as well. Okay, so go through the rules here. And all I'm going to talk about is how I go about actually explaining, you know, what's happening with these rules and try and get them to see it in that same way. I mean, inevitably, some of them are just going to end up remembering a set of rules because they're looking for that shortcut. But the more emphasis we put on their understanding and what we expect of their understanding and what they should be able to verbalise, the better. And so this becomes part of the questioning that I would use in subsequent lessons or revision lessons, or as, you know, part of a revision question in subsequent lessons. So I tend to include these as like little starting quiz questions as well. Okay, right, so the first one, y equals f of x plus a. And I'll give an example here. So really getting them to understand, first of all, what f of x in this case. So what's the base graph? Well, the base graph is y equals x squared. And, you know, I'm encouraging them to see that straight away. So the key thing I think about here is I say, okay, the question I ask every time with all these transformations, and this goes through A level as well, is this graph's going to be affected by, it looks different in this part here, isn't it? X squared plus 3. So I say, okay, what's affected first? Is it the x coordinate or the y coordinate? And the reason I say what's affected first, because the y coordinate inevitably will be affected, but what is being affected first? Is it the x or the y? Well, so I say, well, the y coordinate at the moment is worked out by calculating x squared. We'll run over it. So what's happened here? Well, that y coordinate, which is basically x squared, has had 3 added onto it. So that means all the y coordinates for x squared would have moved up 3 units, wouldn't they? So that means we'd end up whole graph moving vertically in the positive y direction by 3 units. And, you know, I can take it a bit further and say, okay, well, what is that an example of? Because I try and relate this to transformations such as reflection, rotation, enlargement. Well, that would be a translation in the positive y direction. We'll do the same thing with here. So again, I'm not going to do every single one of these, but I'm talking about what affects the y, what's affected first, sorry, the y coordinate or the x coordinate. So that's that one, the y coordinate's affected first. And that means, although this rule's here, they don't really have to remember a rule then. They can just look at it and go, oh yeah, I'll think about it. It's the y coordinates having 3 added onto it. That makes all the y coordinates have 3 added onto it. So like, you know, tracing that original graph, the y equals x squared graph. I'm doing this with a mouse, so this, oh, it's not bad. Y equals x squared graph, and then it's like tracing it and moving up 3 units because each y coordinates have 3 added onto it. So the rules are there as like a little, you know, safety net, but really we want the understanding. We don't want to be relying on that. Okay, next one. This then follows. We're following the pattern of what happened in the GeoGebra lesson. So we can always refer back to those as well. What's happening here? Well, y equals x squared. Well, what's happened here? The value we're squaring here has had 3 added onto it. So what does that mean? That means the value of x that we're substituting in is occurring 3 units earlier. And when I say earlier, I sort of explain that what I'm talking about is from minus infinity to infinity on our x-axis. Not really infinity. Earlier, I mean, if we're plotting it from minus infinity to infinity. So it's happening 3 units earlier than it was before. That means all the x coordinates are going to happen earlier, which means the whole graph's going to occur 3 units earlier, and we end up with this situation here. Much better than actually saying, oh, look, it's plus 3, so I'm going to move 3 units to the left. Not showing any understanding. So what is this one then? Well, it's a translation as well, isn't it? But in the negative x direction. So we can write complicated rules up there, but much better to be able to understand and explain it, I think, rather than having something written down on that. That can be quite complicated, actually. Next one, f of x, affecting the x or y coordinate here. Well, I've used sine x here, so they sketch y equals sine x. What's happened to the y coordinate now? The y coordinate's been multiplied by 2. So all the y coordinates are multiplied by 2. And the reason I use sine x is because you get that stretch in both directions then with that. So that affects the y coordinate. What's happening here? Sine y equals f of a. I mean, you can sort of talk about the functions and make the link to the function work as well. With this sine 2x, well, what's been substituted in is twice what it was. Okay, so means the x coordinate's happening twice as early. Okay, so if we've got sine x, what's happening? Every part of that graph is happening twice as quick as it was before. That means between 0 and 360, and instead of being able to get in one cycle, we are actually going to be able to get in 1, 2 cycles. Okay, so, and you can talk about this invariant point of the y-axis here, because it's actually a bit like if you're going to explain physically what it is, it's like it's being squashed, isn't it, into that y-axis. We could talk about that as being an enlargement, I suppose, in that direction. But anyway, that's what's happening. It's twice as early. Sine of negative 2x. Well, what's happening now? It's a combination of what's just happened before. So we've got what's happened in here. It's twice as early, but then x coordinate, whereas negative is now be positive. It's a bit of a cheeky one, actually, looking at that. I think that's going to need more explanation than just if they've just been thrown in with this and then that comes in. That can be a bit tricky. So I'll come back to that. You may want to change that one if you were using something like this. Because what they've actually missed off here, this is the one I find that students most struggle with, is the f of minus x. And you might need to deal with that separately. So minus 2x, you've got sine of 2x. Even if you did y equals sine of minus x, it might be to do that first, actually, and think about what's happening there. Okay, so what's happening there? Affecting the x or the y. Well, it's affecting the x coordinate, isn't it? So where I'm trying to put in a positive x coordinate, I get the equivalent negative. So basically, the y coordinate that corresponds to this negative x coordinate appears over here. Okay, so for sine x, that means if we just draw a bit of sine x there, for positive and negative, that means, okay, let's use a different colour to explain this. I know you'll probably understand this without any problems at all. So let's say that's minus 30, that's 30. Okay, we're putting an x value of 30 in, but we actually end up getting the y coordinate for minus 30 appearing here. So basically that coordinate is appearing here. And that will carry on, won't it? All of this will appear over here. So all of this, these negative coordinates will appear where we're trying to put in positive and so on. So that's why we end up with this. You can see what's happening. Okay, all the coordinates from negative, in line with the negative x values, are going to appear in the positive half of the diagram and vice versa. And that's why we get that reflection in the y-axis. Worth spending some time on that one, I think, because get your explanation as clear as possible with that. Okay, so coming to the end then, and obviously then you can start assessing, how to use the function notation with this and understand what's actually happening here. With graphs, we don't even know the base graph of, but by understanding what's happening here. Okay, so the f of x is the y coordinate. We've doubled the x, y coordinate, so everything gets stretched by a factor of 2 in both directions. Minus 1, that's still that y coordinate. We're going to move the whole graph down. Again, inside the bracket, what's going to happen here? Well, f of x minus 3, all the coordinates are going to occur 3 units later. And just a point on this, actually, is not to try and do the final graph. I don't think I said that all the way through, actually. It's to draw it in stages. F of x minus 3. Okay, that means that point 3 minus 2 is now going to occur at, what's that going to be? If we're delaying it by 3 units, that's going to be 6 minus 2, isn't it? 4 is going to occur at 7, and the 1 is going to occur at 4. So the first stage of drawing this would be something like this. So I do it in stages. You can just do this in pencil, and the final one, and go over it in pen if you want to emphasize that. And then plus 2 means the whole graph, because that's now effectively the new y coordinate. Okay, that's the y coordinate of this red graph. All the y coordinates are added to, it's going to move up. So drawing in stages is highly recommended. And yeah, combined transformations, same idea. Drawing in stages as we go along here. So you draw the x minus 3 squared, then plus 4. Y equals x minus 3, y equals x squared, y equals x minus 3 squared, then y equals x minus 3 squared plus 4. And then yeah, I usually finish off with some exam question or some exam questions to try and show them exactly what's going to be expected in the exam as well. But more importantly is the understanding. And this lays perfect foundations then for when we go on to completing the square, and being able to sketch and see, how completing the square can also be a brilliant aid to sketching quadratics that, maybe not even, that haven't got any roots. I mean, that's usually the hardest one. Or, maybe the roots are not very nice roots. We've got irrational roots or something like that. Okay, I hope you find that useful. You can let me know what you think of that, or any improvements or anything that you've tried. And thank you for watching. And I will be back soon with another video. Okay, thank you very much. Bye-bye.